Good morning, everybody. Okay, so thank you, Corey. Uh, I started talking about complex functions as mappings, which means if you have a region of a plane and you apply a complex function, what will be the image of that region? Right. So that's what we are talking about these days. And that's the topic of chapter 17, of course. Now, I already talked about uh, linear functions, all right, that look like AZ plus B. A and B are complex numbers. I talked about the reciprocal function, 1 over Z, which will become combination of inversion and conjugation. I talked about Z square. And in general, whatever we did in Z square, of course, we can do for Z cube and in general, Z to the N. And finally, I talked about this Joukowski's airfoil, uh, which was pretty interesting topic. What I did in that Joukowski, uh, I sort of had a bunch of observations what this function does. And then at the end, we put all together and we got some beautiful results. Now, today, I want to talk about first uh, the function e to the z. Okay, exponential function. Well, it's a very well behaved function because to begin with, look, derivative is itself, and e to the z can never be zero. Right away, you say, okay, e to the z is a conformal mapping. Okay, conformal map. Remember, conformal means it preserves the angle and the direction of the angle or sense of the angle. Now, the function e to the z is periodic because e to the 2 pi I is 1. As a result, uh, if we just plug z plus 2 pi I, since e to the 2 pi I is 1, it's the same as e to the z. Okay? So this is called, whenever we have such a thing, it's called periodic function. And in this case, the period is 2 pi I. Now, what does that mean? The period is 2 pi I. That means if we know the behavior of a function, e to the z, in a horizontal strip of width 2 pi I, if we know how this e to the z behaves in this one, we know its behavior on all over the plane, all right, on all over the plane. Because, for example, if you have a point here, you add 2 pi, you go there, 2 pi I, you go there, and you already know its value. So let's concentrate on this then uh, horizontal strip. What happens to x equal a? right? X equal A. Well, in here, Z is A, and then the imaginary part, Y, goes from 0 to 2 pi I. So this is what happens when X is A. When X is A, the modulus, because e to the iy, the modulus of e to the iy is 1, will be this. So all the points of this format will be on a circle of radius e to the a, right? Because the modulus is e to the a. This is what happens then. Okay, this is what happens. E to the a, I mean, this little piece of line, just this little piece of line, when X is A, will go to this circle of radius e to the A. E to the A, okay? How about this horizontal line? This horizontal line, now look, X goes from negative infinity to infinity, of course, but Y is fixed, right? Y is fixed. In this case, this is a complex number, right? Its argument is B, but its modulus is e to the x. And remember, e to the x is never 0. And x goes from negative infinity to infinity. And the image will be this. The image will be this array. Of course, it doesn't cover 0 because e to the z can never be 0, right? Maybe I should just put a little circle here, making sure that this is the array. Okay, this is the array. When x is 0, when x is 0, you get 1 on this array. Here, let's say 1. In this, I'm talking about x going from negative infinity to infinity. When x is 0, you're at this point. When x is on the positive direction of x-axis, you're here in this part, right? This part. How about when x is in the negative direction of x-axis? Well, that is when you cover from the origin to this one. That's when x is negative, okay? So these two are the only thing that I'm going to cover about e to the z. Remember, e to the z, a vertical line goes to a circle, and a horizontal line, after you apply e to the z, goes to this array, okay? Goes to this array. Well, we can always combine these, right? And when I'm talking about a region of xy plane, we can combine this. For example, the question that you might get is this. Here is a region in xy plane, bounded at the shaded area, bounded by negative pi over 4i and pi over I, x equal 1 and x equal 2. The question is, and this is the type of question you are going to see in your problems and also definitely in your next test. So the question is, what will be the image of this rectangular shape when you apply e to the z to it? Well, in UV plane, here's what happens. In UV plane, okay, in UV plane. This horizontal line will be a ray. The angle of that ray is negative pi over 4. So this is the image of course, we know that e to the z is never 0. So again, I'm going to have a little circle here to emphasize that e to the z cannot be 0. Okay. So this line, horizontal line, will become this ray, negative pi over 4. Okay, negative pi over 4. And this horizontal line, again, will be a ray. So in general, the whole horizontal line will be this ray. And in this situation, by the way, whenever you're talking about the image of that region, you better concentrate on the boundaries. All right. So this horizontal line, that horizontal line, we have it. X equal A, x equal 1. Remember, x equal A goes to the circle e to the A. So in this case, it will be E. Okay, here is E. And x equal 2 will go to E squared. It's a circle of radius E squared, okay? Circle of radius E squared. So let's say this is E squared. So the image of that rectangular shape under, if you apply e to the z, it's going to be just this sort of a portion of a washer. Okay, this is the image when you apply e to the z. Okay, so that is what we do in this chapter. We have a region of xy plane, then we apply a function. And the question is, what is the image, right? Any comment, any question about the function e to the z? All right, no question. Then we go back to uh, another function today. So to this list, linear function, reciprocal, z-squared, Jacobi, and I will add WZ. Oh, I call it W, but usually we use the exponential function, exp. I also talked about e to the z function, all right? Yeah. Although doesn't matter, it's exp, exponential function. Now today I want to talk about this function. Okay. This is a very important function, as you will see. And I don't want AD minus BC be zero, because if this happens, the numerator and denominator will be proportional, right? Here is why. If AD minus BC be zero, actually you will have this one, or A over C is same as B over D. If you call it K, A over C, B over D, okay? Then this is what we get. And replacing A and B right there and factoring K, we are getting a constant function. This is not very interesting, right? So the condition AD minus BC not zero is very, very crucial, as you see. As soon as it is zero, that means this fraction will be a constant. Well, this should remind you of 2 by 2 determinants, right? Here is a 2 by 2 determinant. I'm just putting the coefficients in here. Now, when you learned about determinant in the linear algebra, or even college algebra, pre-calculus, whenever a determinant of this matrix 2 by 2 is this, and as soon as this determinant is non-zero, the matrix has an inverse. An inverse of this matrix is right here. This is the inverse of that matrix, okay? So there is a beautiful correlation between the functions that I'm going to discuss today and the matrices. So you can think about this function, right, as sort of this 2 by 2 matrix. And the condition that AD minus BC is not zero, other than making this a constant, the condition when you go to the matrices means this matrix has an inverse, and its inverse is right here. Okay? Here is its inverse. Well, because of its significance, this function has a name. We call it linear fractional transformation. all right? Linear fractional transformation, and or Mobius function, okay? As before, remember what I did with Joukowsky airfoil, that function. I am going to do the same thing here. I'm going to find a bunch of observation. Let's start with taking its derivative. Derivative of this function is right here. And remember, we said AD minus BC is not zero, right? So derivative is never zero. When derivative is not zero, the function as a mapping is conformal mapping. That's the first observation. It's always good to know that. It's always take derivative and see if the function is conformal or not. So this function is conformal. Now, here's observation number 2. The inverse of this function is also a linear fractional transformation. Why? Okay, remember in college algebra, how do we find the inverse? Call this one W, cross multiplication, and solve it for Z. I guess so. Yeah, but that is, of course, in topological spaces when we talk about Mobius strip. There is also a connection there. Anyways, finding the inverse, you cross multiply and then solve it for Z. When you solve it for Z, you see, here we go. It is again, now the variable is W, right? So so the inverse also is a Mobius function. Okay, it's good to know. Observation number 3. How about if we compose 2 linear fractional transformations? Okay, here is one. I call it F. The coefficients are, of course, could be different. That's why I have A2, B2, C2, D2 here. How do we compose these two? Well, here is F of G of C. So in F, you replace all the Z's by G of C. That's how we compose 2 functions. So in F, you have A1 times this plus B1. Then C1 times again this plus D1. Here we go. Well, to simplify, I'm going to multiply by this denominator and divide by the same denominator. If we go ahead and simplify, this is what we get, right? You factor Z, you get a number times Z plus a constant divided by a number times Z plus a constant. So composition of 2 linear fractional transformation is also a linear fractional transformation. Why do I need these observations? Oh, you will see momentarily. Here comes observation number 4. In observation number 4, there is a concept called fixed point. Fixed point of a function. The definition is pretty obvious. We say x0 is a fixed point if you plug x0 in, and the result also be x0. If such a thing happens, we say that x0 is a fixed point. Doesn't change, all right? The function doesn't change x0. x0 will be. Now, in Mobius function or linear fractional transformation, I want to show that this function has at most 2 fixed points. And here is why. What are the fixed points of this function? When you plug in, you get the same result, right? The same number, which means this. And by the way, that is how we find the fixed points. F of z got to be equal to z. If you multiply this out, I mean cross multiplication, will give you this quadratic equation. So fixed points are the solution to this quadratic equation. And a quadratic equation cannot have more than 2 solutions, right? We only have 2 solutions for a quadratic equation. At most 2. Sometimes we have 1. Okay, that is a good observation. Any linear fractional transformation has at most 2 fixed points. And now, here is the major theorem of this topic. I'm going to prove that any linear fractional transformation is completely and uniquely determined by 3 points, 3 inputs, and the images of those 3 inputs. So if you have 3 points and the images of those 3 points, that's enough. We can figure that Mobius function. Here is the proof. Why 3 points are enough? Suppose we know that if you plug Z1, we get this number. Plug Z2, we get this number, and I'm going to show that having this information, we are going to have exactly one Mobius function that does this. Well, proof by contradiction. Suppose there are 2 functions that they do the same thing. Here is proof by contradiction. Suppose we have 2. One is this W. The other one, let's call it S. Okay? S is another Mobius function, does the same thing. Well, the inverse of S is also a Mobius function, right? That was observation number 3. The composition of 2 Mobius function is Oh, that was the observation number 2. This one is observation number 3. So if I consider the inverse of S and compose it with W, this is again a linear fractional transformation. But let's see what this linear fractional transformation does. If you plug Z1, W of Z1, oh, is W1, and the inverse of W1 is Z1. So that is a fixed point because we plugged Z1 in and we got Z1. You do the same thing with Z2 and Z3. So this composition is a linear fractional transformation, but it has 3 fixed points. All right, 3 fixed points, and that can never happen. That can never happen. So if you have 3 distinct points and their images, those 3 distinct points and their images will uniquely determine that linear fractional transformation. Okay, this is very good, and here we have now an algorithm to find a linear fractional transformation. So remember, if you have 3 points and their images, we can construct the linear fractional transformation in this fashion. Well, this is if you plug Z1, oh, this is a number, right? And this is a number. But if you plug Z1, you get 0 on the right-hand side. This cannot be 0, so this has got to be 0. That means W is W1. Yeah. So if you plug Z1, you get W. Same reason, if you plug Z2, you get W2, and so forth. All right. So here is an example. You're going to have a bunch of examples like that and problems in your homework sections and also in the test here are 3 points. I want to find a linear fractional transformation that sends 1i negative 1 to 1 negative 1 0 1. So here is Z1, Z2, Z3. Here is W1, W2, W3. You replace this in this formula, okay? So W minus W1 will be W plus 1 divided by W minus W3, okay? And this is going to be a number. Same thing on the right-hand side, you get this. And now you go ahead and solve this for W. That, okay? Solve that for W. Here's what we are going to have. This negative 1 just goes right there. And if you multiply this, by conjugate of the denominator, you get 2 here and 2i on the numerator. So the right-hand side will be this. Now you cross product and solve it for W. If you go ahead and do the rest. Here is the function. Here is the function. Okay? So that formula, whenever you have 3 points and the images, will produce the linear fractional transformation. And of course, you got to do a little bit of manipulation, all right? Is this the only way to find? Of course not. Of course not. We can do it, be very creative. For example, look at this. I'm doing it in different way now. So I want a function that sends I to 0, 1 to -1, -1 to 1. As soon as I goes to 0, the numerator should look like z minus I. All right? Now this function, if you plug I, numerator will be 0, so it's 0. So we used this one. Next, if you plug 1, you're supposed to get -1, right? 1, -1. That gives you this. If you plug -1, you got to get 1. And that gives you this equation. So 2 equations with 2 unknowns, you solve this for C and D. For example, if you add them, you get 2D, whatever, and that is your D. And as soon as you get D, plug it in here, you get C, all right? C is I. Here we go. All right? So, although that formula theoretically is correct and gives us the result, but that's not the only way. In mathematics, there is no, when you have a problem, there are different ways of solving that problem, right? I don't want to restrict your creativity, so you can do your own way, but of course you got to be use logic, mathematical logic. Okay, here is what I said. There is a sort of connection between linear transformations and invertible 2x2 matrices. So the inverse is this one, right? The inverse of A is this one. So look at this inside the matrix. You get these numbers, but of course, this is the 1 over determinant of the matrix, okay? Now, we can establish some sort of relationship between these two by saying that, okay, look, as soon as you have a linear transformation, phi of that is this. Okay. Now, this is sort of function that goes from two algebraic structure from one to another one. The structure that we impose here is composition. The structure that we impose here is product of two matrices. Product of two matrices. So what this function does, if we apply it, it preserves the operation. So if you compose two linear transformation, phi of that will be product of these 2 by 2 matrices. Okay. Anyway, that's a little just giving you information about the two algebraic structure. Anyway, Brandon is asking, how did you get C plus D? So based on requirement, if I plug 1, I'm supposed to get -1, right? Negative. So in here, let's plug 1. If I plug 1, it will be 1 minus I divided by C plus D. So if I plug 1, I'm supposed to get negative. Okay? Now you cross multiply. So this C plus D, negative, fine. I could put it in denominator, right? Is 1 minus I. Or C plus D is negative one minus I. Multiply both sides by I. All right? Good. Okay, let's see. Oh, I'm still going to talk about this linear fractional transformation. So far, with certain observations, we found certain facts. But now, what about the mapping? How does this behave when it is the question of mapping? The first observation is, we call it theorem fact. If you apply this to a line or a circle, that could be a line or a circle. All right. Now let's see why. So this function maps lines and circles to lines and circles. Oh, that doesn't mean a line is going to be exactly a line. No, a line can be a circle. The map of a line can be a circle. Or a map of a circle can be a line, all right? But the totality of lines and circles will be mapped to lines and circles. Here is why. This function looks like this. If I sort of do a little bit of algebra, it's a constant plus this number times this. When we add a constant, we talked about linear functions. We know that adding a number doesn't matter. Line goes line and circles goes circle. Multiplication by a number, same thing. It is the reciprocal function that we need to check. So it is the reciprocal function that we need to check and make sure that the reciprocal function sends line and circles to line and circles. All right. So in XY plane, here is an equation of a line and circle. If A is 0, you will get a straight line. If A is not 0, you will get a circle. Okay? So that's in general a line or circle. What happens if we apply 1 over z? Apply 1 over z to this. Well, let's do a little manipulation. We know that this is modulus of z squared, right? So it is a modulus of z squared, which is z bar, x. If you add these two, you get x. Here is x. If you subtract these two, you get y. Okay? And here is d. So I replace this one by z bar, this one here, and this one here. So that is the equation of a line or circle in terms of z and z bar. Oh, here, I assume, Del Dodson, you are talking about this denominator. It's CZ plus D. Oh, yeah, this part. Oh, yeah, I see. There is a typo here. Good eyes, good eyes. Of course, it is the good eyes. Okay, good. All right, anyways, going back to this, now, this is the equation of the same equation in terms of the z bar. And now we apply that reciprocal function. Reciprocal function, remember, I am worried about this. So z will be 1 over w. Now it is time to replace z by 1 over w. So here becomes, all right, this is what happens. Now, to get rid of this WW bar in denominator, we multiply everything by that WW bar. This is what we get. And this is equation of in UV plane. Remember, W is U plus IV. And if you replace W by U plus IV, this is what we get in W plane, which is equation of either a circle or a straight line. If D is 0, you get a straight line. If D is not 0, you get a circle, okay? So I don't want you to get lost in technicality, but it's good. It's good to see the reasoning once in your life. So this is the theorem. From this point on, we know that this function sends line and circles, the totality of lines and circles to lines and circles. Okay. Now, let's see what else. Well, I'm going to give you an example here. This is in general, a Mobius function or linear transformation, linear fractional transformation. It seems that we have 4 unknowns, but actually it's not, because as soon as one of them is non-zero, we can divide by that constant. So in reality, we have only 3 unknowns to take care of. And that is why 3 points and their images will be enough. Okay? Now, here, if you plug infinity, by which I mean taking limit as v approaches infinity, it's a over c. Right? If denominator be 0, you will have infinity. So from by these 2 conventions, if you plug infinity, you get a over c. If plug negative d over c, denominator will be 0, we get infinity. By these 2, things will be a little bit interesting. As an example, here is an example. I want to find a linear fractional transformation that sends 0 to 0, I to 1, infinity to 2. Okay? As soon as you say it sends 0 to 0, well, look at this. If you plug 0, you're supposed to get 0. Then that means B is 0, right? B is 0. So that's what happened. If you plug 0, B is supposed to, and when B is 0, you get this. And this is what I meant by, if you divide by A, or by C in this case, you get a constant here, a constant here. So now we are in the finding these 2 constants, all right? So I can write it AZ divided by Z plus D, and finding A and D. Okay? So the condition that says infinity gives me 2, infinity gives me 2, if you plug, I mean taking limit, A over D, the limit is just A, so A is 2, done. Right? A is 2. So we are end up to having this, only to find D. And the third condition will help us finding D. All right. So it's not really that bad. Here comes infinity. A over C is 2. This is another way of doing it. So here, and then we use I. We should produce 1, plug I, you will produce 1, that gives you D, and here is the answer. So this is the Mobius function or linear fractional transformation that sends 0 to 0, infinity to 2, and I, if you plug I, you get 1, right? Good. You are going to have a question like this in your next test. I will give you 3 points and their images, and I will ask you to find that linear transformation. Okay. Now let's see what does this linear fractional transformation do as a function. And this is the most important properties of this Mobius function. I would like to map upper half plane onto this, with x-axis being the boundary. As a result, x-axis will be mapped onto this unit circle, okay? This is what I want to do. I want to have this upper half plane onto inside this disk, okay? It's a beautiful mapping. A function that does that is extremely important. Okay, here is the first one. Well, I want this x-axis be the bond, which is boundary here, be boundary here, right? So every point of x-axis should be mapped into the circle, which means its modulus is 1. So here is 0, 1. So t of 0 is 1. T of infinity also is 1. Infinity, I mean here, as in x approaches infinity or z approaches infinity. So that means b over d, modulus of b over d, if you plug z 0, it will be modulus of b over d is 1, and infinity gives us a over c. Modulus of a over c is 1. All right? So b over d, a over c is 1. But a over c means, anytime you are dealing with a fraction, its modulus is modulus of numerator over modulus of denominator. So that means modulus of A is the same as modulus of C. The same thing here, modulus of B is the same as modulus of D, okay? And if you divide these two, this is what you get. B over A and D over C. B over A and D over C have the same modulus. So if I factor A from numerator and C from denominator, this is what I get. But I know modulus of this is 1, all right, based on the modulus of this 2 are 1, these two. Also, I know that A over C here, modulus of A over C is 1. So this looks like e to the I theta or e to the I alpha. So by this little observation, this is what the result gives me. I know that it will be a number like this, e to the alpha, times, let's say, This is the Z0, this is Z1. All right. And we know that modulus of these two will be 1. Then comes this point 1. What about this? Well, if I plug 1, again, the image has to be on this unit circle. So the modulus, if I plug 1 in, if you multiply this out, this is what you get, right? This is 1 and 1 that goes out. So this equals that one. But when you add a complex number with its conjugate, you get the real part. So all I know right now is that the linear fractional transformation looks like this. What about this Z0 and Z1? I know that the real parts are the same. Oh, let's continue. When the real part is the same and there are on the unit circle, the imaginary part should be, here is what we know, Z1, and the real parts are the same. When the real parts are the same and we have equality, that means these two are the same. Oops. So imaginary of Z0 is plus minus imaginary of Z1, okay? But if you imaginaries be the same, so this two numbers will be the same, that doesn't give us anything. It will give us a constant. But we better have one negative of the other one, right? One negative of the other one. So this is, in general, the format of linear transformation that maps upper half plane into this unit circle. Now, I'm going to make it even easier. I will take this one as 1. Since Z0 is a point in the upper half plane and has to go to the 0, I'll take it I. Here we go. Oh, this is the most important linear fractional transformation you need to know. What does this do? It sends upper half plane to this circle. How? Well, this 1/2 A goes in the upper part. This part, the first quadrant, goes to the lower part. Okay? Please remember that. It's very important. So by this function, we can send upper half plane, any half plane, I will tell you how, any half plane, especially upper half plane, to the circle, to this disk. The inverse will send this disk to upper half plane. What is the inverse? Here is the inverse. You know how to find the inverse. You must cross multiply and solve it for Z, okay? This is the inverse that sends the upper half plane into the disk. Okay? Here's the function. So this is the sort of the beautiful conclusion of this linear fractional transformation. And now we can do a bunch of different examples and I'm going to give you, right. So we know this happens. We know this guy sends upper half plane to this unit disk. Now here is an example. This is the kind of questions you are going to get. I have this S described. You need to map it. The set of all x, y's that x is less than or equal -1. Less than or equal -1 is this. This is S. Okay, here is -1. I want to map this onto unit disk. Okay, onto unit disk. Well, we know this one goes to unit disk, but how do we take care of this? Well, here is how. First of all, I am going to rotate the whole thing. Rotate in this direction, which is clockwise, 90 degrees. If you rotate this 90 degrees, you get here. Okay? How do we rotate 90 degrees? By multiplying by e to the -pi/2i, which is thing. So if I multiply z by -iz, this s becomes here. Then bring it down one unit. And that is when you say z minus I. Here. So after these two operations, now we have the upper half plane. Now you can apply that function and go through the disk, okay? So composition of these three motions. One motion is rotation, another motion, bring it down, and the third one, applying this. So here we go. Motion number one, you multiply by -I. Motion number two, you subtract I, bring it down. Motion number three, you send this here. So you replace in a z by this. So here we go, right? So this function maps this S into unit circle. Isn't that fun? No, it is fun. Now we can play with these mappings. Now we can rotate, we can translate, all right? And if we apply this function, we can take upper half plane into a unit disk conformally, because everything was conformal, okay? Let me give you another example, because I really want you to be get very good at this. So here's another example. I want to, this is a region of XY plane. It's given you the set of all ordered pairs that x and y satisfy this equation. How do we find S? Well, that's part of college algebra, isn't it? You go ahead and graph x plus y equal square root of -2. And after graphing it, here, this line is x plus y equal square root of -2. Let me write the equation on top of it. Okay. This is x plus y equal. The line itself is this. But this line is going to divide the plane into 3 parts. On the line, you have equality. So we have this side and this side. You choose a test point, 0, 0. Plug it in here. It says 0 less than or equal that, which is nonsense. So the part that contains 0, 0 is not acceptable. This is where the set of all x, y's such that x plus y is less than or equal to the square root of negative square root of 2. This is the part. Now, I want to go ahead and map this half plane into unit circle, unit disk. Oh, the first thing I need is sort of a rotation. If I rotate clockwise, going this way, with this angle, which is 3 pi over 4, I get here. So the first motion is the multiplication or by this, which is a rotation. The next one, you bring it down, make it upper half plane. Okay, you bring it 1 unit down, make it the x-axis here. And that's when bringing down, translating down, you just subtract I. And after you have this, then you apply this famous function, and we know that it takes you to the unit disk. So here, again, we had 3 motions: rotation, translation, and then applying this function. Composition of these 3 is right here. The first one, you take z, rotate z, subtract, bring it down, and now apply that. So here's the function that works for us. Any comment, any question? Anytime we want to rotate, we actually change the angle, right? We change the angle. So in general, let's say